This is day 10 of the probability unit for Math for Life. So the first thing we need to do is go over some vocabulary words and what they mean. So the first one says an experiment is a solution involving chance or probability. An experiment has a set of possible outcomes or results. So for instance, an experiment, say we want to know the probability of getting heads or tails on a coin. The experiment would be the actual flipping of the coin, say 50 times or 100 times, to figure out what the probability is. So an experiment is the actual doing of something to find out the results or possible outcomes. The next vocabulary word says a random variable is a variable whose value is determined by the outcome of a random experiment. Each value of a random variable can be associated with its corresponding probability. So random meaning exactly what it means, to just kind of pick from the choices randomly, and variable meaning giving it an X, Y, Z kind of a label. The next vocabulary word says a discrete random variable is one whose set of assumed values is countable, meaning 1, 2, 3, etc. So not like 3.7, 99, negative 300 and whatever. They have to be countable, so in an order that is counted. And then a probability distribution is a mapping of all the possible values of a random variable to their corresponding probabilities for a given sample space. This can be represented as a table or a bar graph. So really the probability distribution is what it looks like on a graph. We're going to talk about different probability distributions on the next note-taking guide, but today we're just going to kind of graph them and see what they look like. So here's our first experiment, flipping two coins. We're going to let the random variable x be defined as the number of heads obtained. And we want to know if that's discrete. Well, discrete would be countable. Can we count the number of heads obtained? Well, we probably can, so it's probably going to be discrete. But let's kind of look at it and see. So it says first, let's make a probability distribution table and a graph for the random variable x. So I want to talk about, first of all, what happens when you are going to flip two coins. And what the number of heads obtained is. And we know we're flipping two coins because that's what we said we were going to do. So if I flip two coins, I have the probability, or the possibility I should say, of getting a heads and a heads. I have the probability or possibility of getting a tails and a tails. Or I could have a heads and a tails, or a tail on the first coin and a head on the second one. So these are the only four ways that I can flip two coins. So again, X is the number of heads obtained. So we're going to look over here and fill in our chart. So the heads obtained here is 0. So how many times do we have the chance of getting 0 heads? Well, that would be only where we get tails, which means we're going to have the probability of 1 out of 4 different chances for that to happen. What's the probability then over here? It's asking of getting 1 heads. Well, you could have 1 head here, you can have 1 head here, so that's 2 out of 4, and 2 out of 4 will reduce to be 1/2. And then the last one is, what's the probability of getting 2 heads? The probability of getting 2 heads is 1 out of 4 again. Those probabilities add up to 1, which is what they have to add up to be, meaning we've taken care of all of the different probabilities that can happen. So now we're just going to graph these. We've formed some ordered pairs here. Our first ordered pair is 0 and 1/4. So we're going to go and graph that ordered pair. When you're at 0, you're up at 1/4. 1/4 as a decimal point number is 0.25. 1/2 as a decimal point number is 0.50. And then again 0.25. So when we're graphing these, we're going to graph according to their decimal point values. So at 0, we're at 0.25, so we're like right here. And then at 1, we're at 0.5. I didn't notice that we started with 0 over here, so I'm going to move my mark over to here instead of where it was at. That 0 is counting for the y. I needed the 0 that was counting for the x. And then over at 2, I'm up 1/4 again. So again, up at 2.5. So here is the probability distribution of what it looks like. So what it looks like on a graph. So it says down here, just to remind you, we could have picked our random x variable as anything. We picked it to be the probability of getting a heads, but we could have picked it as the probability of getting a tails. We could have named that anything we wanted to get these random probabilities. All right, let's look at our next example. This probability is an experiment of rolling one die, and it says let the random x be defined as the number that lands up. So if we roll one dice, we have a chance of getting a 1, a 2, a 3, a 4, a 5, or a 6. So the probability of the number landing up would be the probability of whatever it is that lands up. So the probability of getting a 1 would be 1 out of 6. The probability of getting a 2 would also be 1 out of 6. Probability of getting a 3 is again 1 out of 6. 1 out of 6, 1 out of 6, 1 out of 6, because each number has an equal probability of landing. So when I graph this, I'm over 1, and I need to figure out what decimal point number 1 over 6 is. So I can figure that out by just doing 1 divided by 6 on my calculator. And then that decimal point number, when you do 1 divided by 6, is 0.1666. So 0.1667 if you wanted to round. So we're up here, maybe right here. For 2, we're still in the same spot. For 3, we're still in the same spot. 4, still in the same spot. 5, still in the same spot. 6, still in the same spot. So if I were looking at the way this was distributed over here, it didn't change for any of my different outcomes. And we're going to talk about what kind of a probability distribution that is tomorrow. But for today, we're just figuring out the possible outcomes for probability distributions. So here we go. Here's another one. All right, this time we're figuring out the probability of rolling 2 dice. And this is just a chart up here that kind of shows you what that probability is. So your choices when you roll 2 dice here would be, the smallest total you can have is 2. Because if you roll 2 ones, you get 2. So, and then the next total you could get would be 3 and 4 and 5, 6, 7, 8, 9, 10, 11, and the highest number you could get would be 12. That would be double 6s on your dice. So how many times can I get a 2? I could only get that 1 out of the total number of probability chances that there are, which is 36. The same thing down here on the 12, that would only be 1 chance out of 36. Then if I went to my 3s, those are my 2 options for getting 3. So 2 out of 36, which I could reduce, but I'm going to leave it 2 out of 36. I also get the same probability down here on 11, which is 2 out of 36. Then I go on to the total that adds to 4. So a 3 and a 1, a 2 and a 2, and a 1 and a 3. So 3 different ways out of 36 total ways. And I'm going to jump down here and look at the opposite side because I see that I've got a pattern here going on here. If they add to the number 10, that's 3 out of 36 different ways. Coming back up to looking at the numbers that add to 5, there's 1, 2, 3, 4 of them. So 4 out of 36. Also coming down and looking at the ones that add up to 9, there's 1, 2, 3, 4 out of 36. Doing the 6s right here on this column, 1, 2, 3, 4, 5 out of 36. which is also going to be the same on the 8s. And then the highest probability of rolling a number would be rolling a number 7, and that would be 1, 2, 3, 4, 5, 6 out of 36. Now if I took the time to add those straight down, they would add up to 36 over 36, which is 1, and it always has to add up to be 1. So then I'm just going to graph these as decimal point numbers. And if I do 1 divided by 36 on my calculator, that's a 0.027. 0.027. So at 1, I'm 0.027, which is not really very far up. I'm also that same thing over here at 12, because if you notice, my values for 2 and 12 are the same. And I guess I just graphed that again in the wrong spot, because the first number that we even have a chance of getting is 2, so it should be right here at 2 instead. And I guess my probability of rolling a 1 would be 0. I didn't put that on my chart, but I could put it there at 0. All right, 2 out of 36 then is 0.55, so this one's 0.55. So it should be a little bit higher than that other one, going a little bit higher on this one. Then I'm doing 3 divided by 36, which is 0.8. So again, just a little bit higher. And then 4 out of 36 is 0.11. So I'm a little bit above right here. And then 5 divided by 36 is 0.138. So a little bit higher than that even. And then 6 divided by 36 is 0.167, so a little bit higher. So this, if I were to look at the probability distribution of this, I kind of have this mountain that's being formed right here on my probability distribution. So just another way to see it. So this one is kind of forming this symmetrical mountain over here. On the last one, we just had that straight line that went across the values. And on the first one, again, it kind of looks like it might be symmetrical or find a mountain on one side or the other. All right, let's see what we've got for this last one here. This one says on experiment 4, it says flipping 2 coins. So it says let random, I'm not sure why we have the dice here when it says flipping 2 coins, but let's read it and see what happens here. It says let the random variable x be defined as the difference between the 2 dice. So that's the problem up here at the top. This is just titled wrong. We're actually doing the 2 dice again this time. So my friend who made this worksheet we just didn't get that fixed at the top. But we're actually, if we read it, it says let the random variable x be defined as the difference between the 2 dice. So this time we're subtracting the 2 dice. So if I subtract 1 and 1, I get 0. Also, if I subtract 6 and 6, I get 0. So I have 2 out of 36 possible on my subtraction to get 0. Now if I subtract to get 1, I would have these 2, and then these 2 also over here subtract to be 1. So 2 plus 2 is 4. So 4 out of 36 on this value. My next one's on my dice to subtract to get 2. So 3 minus 1 would get me 2. Also 3 minus 1 right here would get me 2. 6 minus 4 and 6 minus 4. So that's again 4 out of 36. Which means I might have missed some because I thought that they were going to have a pattern and they don't have a pattern. So maybe we should go back and look at our subtracting to 0 again. Is there any others that will subtract to 0? There actually are. So you know what? I'm just going to start over on this, because sometimes when we're doing an experiment, we're going to find that we make an error and we're going to have to start over again. So you can start over again, or you can just write out to the side again. So let's go back and look at the ones that will subtract to be 0. 1 minus 1 is 0, and 6 minus 6 is 0. But we also missed a bunch in there that I didn't think about. We have 2 minus 2, which is 0, 3 minus 3, which is 0, 4 minus 4, which is 0, and 5 minus 5, which is 0. So we actually have 6 out of 36 to get 0 when we subtract them. All right, let's try the next one and see if we can get a different value for subtracting to be 1. So I'd have 2 minus 1 and 2 minus 1 again would get me 1. I also have 5 and 6 here and 5 and 6 here. And then let's look and see if we can find any others that will subtract to be 2. Here's 6 and 4 and 6 and 4. Oh, I'm not doing 2s yet. I'm getting ahead of myself, you guys. I'm still doing 1s. So let's see if any others will subtract to be 1. Oh, here's a 5 and a 4. They will subtract to be 1. Here's a 5 and a 4. They will subtract to be 1. Here's a 3 and a 4. They subtract to be 1. A 2 and a 3 right here. They subtract to be 1. A 3 and a 2. And a 3 and a 4. So this is looking like there could possibly be a pattern on the way that this happens, which would be helpful if there is. So how many did I find that will subtract to be 1? I found 2, 4, 6, 8, 10. So 10 out of 36 that will subtract to be 1. Now I need to go to my next one and find the ones that will subtract to give me a value of 2. So 3 and 1, 2 and 4, 5 and 3, 6 and 4. Also 1 and 3 over here on the same column. It looks like we're going to get 2 all the way down. So I have 8 out of 36. And then let's go to our next number and see what we can do there. So let's go and do, that will subtract to be 3. So that will, this one will, that one will. Also other side the same. So 6 out of 36. If I go to another one, then I need them to subtract to be 4. So 5 and 1, 6 and 2, 5 and 1, 6 and 2. So 4 out of 36. Subtract to be 5 is our next one. So we're subtracting to be 5, which is 6 and 1, and 6 and 1. So that would be 2 out of 36. And then none of them will subtract to be 6, and none of them will subtract to be 7. Now if we add those straight down again, you guys, they still do add to the number 1, so we know that they do work. And then I'm just going to graph these so that I have the values there for the graph. So 6 divided by 36, just punching that in my calculator, that's 0.1666. So at 0, I'm 0.1666, which is approximately there. Okay, if I do 10 divided by 36, it's 0.277. So to get a 1, I'm at 0.277, so about up here somewhere. Then I do 8 divided by 36 on my calculator and get 0.22. So right in here somewhere. 6 divided by 36, which is 0.16. So around there again. 4 divided by 36, which is 0.11. And 5 would be 2 divided by 36, which is 0.5. And then 0 and 0. So this is a little bit different than what we've seen before because we're starting high and going down low for our distribution here. So these are different ways that we have distributions when we look at our graph. Again, we'll talk a little bit more about these later, but this is how we find the possible outcomes and we distribute our probabilities. Good luck with your homework, you guys.